Hey there, awesome physics students. Let's talk about what controls the speed of a wave. We have a fundamental relationship between the velocity, the wavelength, and the frequency of a wave. And this seems to strongly suggest that if I increase the frequency of the wave, then I will be able to increase the wave speed the same amount. And remember that the frequency of a wave is determined by the frequency of oscillations of the object that's causing it. So let's see if that's true. So let's see if our idea of increasing the frequency to increase the wave speed will work. First of all, let me just change some of the settings here. I have no end. And let me reduce the damping here. And let me just take this wrench and pull it up and down and create some waves. And you can see the wavelength of those waves nicely. And let me just stop and I'll try and increase the frequency and see what happens. So I'll go back up and down a little more often. And you can see that actually it looks like it's going to change the frequency. So let me do this in a more organized fashion. I'll turn it on oscillate. And right now, if you look at the frequency down at the bottom here, this is 1.5 hertz, and it has a certain wavelength. And I can even turn on some rulers and take a snapshot in time to look at the wavelength. And if I look at one full wave from about here, that's about 1 3/4, to about here, that's about 5 3/4. That looks like the wavelength is about 4. So let's go ahead and change the frequency. I'm going to increase the frequency. I'm going to double it because I want to see a dramatic effect here so I can see if the waves are traveling faster or not. So let me just try this again. I'll turn it back on. And you can definitely see that the wavelength looks like it's decreasing. Let me just pause it here and see if I can measure it. So it looks like the wavelength, here's one full wave from about 2 to about 4. That means the wavelength has actually gone down to about 2. So unfortunately, it seems that as I increased the frequency, the wavelength decreased. And so when I doubled the frequency, the wavelength went down by half, and that suggests it keeps the speed exactly the same. So I don't think this is going to work because of this. It looks like those two are compensating for each other. So let's try something totally different here. Let's change this to pulse mode, and let's see if we can play with some of these ideas down here. Just the amplitude and the tension. I don't want to worry about damping right now. So I can send a pulse here and see, and just visually watch it and see what happens if it speeds up or slows down. So let's, right now the tension is on high. So let's turn the tension down and try again. And it looks like that pulse looks slower to me. Let's try another one. That pulse, that pulse looks a little slower. Let's turn it way down and see if that really decreases it. Yes, that definitely has an effect. So it seems like the tension, which if you recall from oscillations is the restoring force, that is affecting the wave speed. Okay, let me just turn the tension back up to normal here for our next experiment. Now let's try to change the amplitude. That would be the height of this pulse. Let's see if that has an effect. So let's see, let me turn it way down. This is going to be a really short pulse. You can see that speed of that wave. And let's turn it back up and see if that makes a difference. No, that doesn't really seem like it makes a difference here. Let me turn it way up to see if I can see. I mean, it's definitely going higher. That's a difference, but it doesn't seem like it's making it to the finish line a little quicker. And if I wanted to get really particular about this, and I have a timer I could put on, but I think I can just see from looking at it that it doesn't look like it has a really noticeable effect. If I increase it or decrease it, it doesn't seem like it's affecting the speed very much. So it seems that idea did not work. What we saw is if the frequency was increased, then the wavelength would decrease in the exact right amount so that the velocity would stay the same. And so they are just compensating for each other. So this equation is not useful for controlling the speed, but it is useful for telling us about the speed and the wavelength and the frequency. What really controls the speed is what we saw with oscillations. That is, it's a square root of some interplay between a measure of restoring force over some measure of inertia. So really, it's the properties of the medium that dictate the wave speed. For waves on a string, the measure of restoring force is the tension in the string, and the measure of inertia is the so-called mass density, or the mu is the letter here, that we're using. So mu is just the total mass of the string divided by the total length. You can think of this as like the mass per foot. It's the mass taking into account that longer strings will have more mass. So that's what dictates wave speed on a string. In general, it's always going to be some measure of restoring force to some measure of inertia for all waves, no matter what type they are. In general, it's got to be the properties of the medium itself that dictate the wave speed and not the frequency or the wavelength.